maybe this is just my stupidity and my confusion, so please excuse me for that. I always got confused by that. You have a wave and a particle. Let's do the simplest non-relativistic case, and this is a hidden variable theory. We see the particle, so the hidden variable is a wave. The distribution probability should be on the wave or on the particle? Where am I confused?
So you see the particle, but not in complete detail. You will see, for instance, in a two-slit experiment, you fire the particle, you see where it lands, okay, to some accuracy. You don't see the trajectory on the way. You don't see, well, how did it move to get there? If you do make certain measurements to try to see, well, how did the particle move in between being fired and landing at the backstop, then you start changing the wave function because you introduce a Hamiltonian, you change a Schrödinger equation, and you're no longer looking at the same setup in the sense that if I want to know, look, here's a given wave function, evolution, and I want to know how did the particle move for that given wave function evolution. I can't start coupling Hamiltonian because I'm going to change the wave function evolution. If I do couple Hamiltonian to measure the position, well, I'm going to do that, let us say I do that at the final time. And now, as you know, that effectively affects the wave function. So, I mean, I don't know if that's maybe a bit of a ramble, but the point is, one often hears it said, look, it's a misnomer to say that the particle trajectories are hidden. Surely it's the wave function that's hidden. Bell, I think, took this or made statements to that sort of effect. I think it's a bit. It's in a way it's partly true, but it's also inaccurate. You do not see the details of the trajectories for a given wave function. So in that sense, maybe it would be more precise to say that the details of the trajectories are hidden.
But they don't see the wave function either.
So the wave function is something, I mean, it is a theoretical device that a given preparation, the Schrödinger equation tells you that for a given preparation there will be a certain wave function. You need to assume the truth of the Schrödinger equation in order to manipulate the wave function. So there's a kind of theory dependence here, if you like. One can get into issues of, well, do we see the electromagnetic field? Well, you use our knowledge of electrodynamics and Maxwell's equations to deduce that, this light thing that's going on in my eye is somehow that there's a field going on through space. So you might say that, I mean, everything, these things, there's some component of a theoretical construct here, which is supposed to mirror reality. Anyway, the details of the trajectories are hidden. So in that sense, I like to say it's fair enough to call them hidden variables.
I have a question in regards to your intriguing suggestion that the Bohm interpretation can explain why we see too little power in the Planck data on large scales.
Yes.
So I'm curious, another thing that we can measure very accurately also in the cosmic microwave background is the extent to which the fluctuations are what we call Gaussian. So for the non-cosmologist in the audience, the deal is basically that these quantum fields in Fourier space look like harmonic oscillators, and we all know that the harmonic oscillator has a wave function in this ground state, which is Gaussian. And I'm very curious, can you, in addition to that prediction of a power deficit, also make some prediction for what kind of non-Gaussianity that we should measure?
Yes.
Because that would be really interesting.
Yes. So there's something in this theory. In principle, the initial distribution could be anything. There's no, it's like if I take the thermal analogy. If I'm going to say I'm going to consider molecular configurations and not in thermal equilibrium, well, they could be anything. They could all be bunched in one corner. They could be, So there's a sense in which, in this theory, you have to sort of deduce what the initial distribution was from data. But of course, we don't want to just be curve fitting. We want to make some kind of prediction. Now, in principle, the initial distribution, it could be non-Gaussian, it could be non-isotropic, it could have, power deficits, it could have anything. What I've been looking for is there some feature that would sort of emerge naturally from the dynamics? Is there something, and what we've looked at the beginning is this simplest case where all I'm going to be looking at is the width of the distribution. Is it, is it larger or smaller than the quantum width? So in other words, the power. And it turns out that there is this kind of natural suppression at larger scales, so I would expect to see a smaller width above a larger scale. If you ask me what would I expect to see about non-Gaussianity, I haven't studied it enough. It's kind of one of the next projects. Certainly, I mean, it's certainly true that non-equilibrium can give you non-Gaussianity. It seems from the latest data that there's no good evidence for non-Gaussianity. It seems pretty Gaussian. So, I'm starting to think about, well, is there a reason why the Gaussianity will have disappeared, or is there a good reason to assume that initially I do have Gaussianity, but with a width that is different from the quantum? These are questions that it needs to be explored. What I can say, and I'll go into a bit on Wednesday, is that the Planck data has also, there seems to be some evidence for anisotropy at large scales. And of course, this non-equilibrium, it could be anything. It could be anisotropic. And there's an interesting point that if in this kind of model where the short wavelength modes relax, the long wavelength modes don't, if I began with a state that was anisotropic, then I think I've understood enough to say it's pretty clear that the short wavelength modes would come out to be isotropic because they relax to equilibrium, and the long wavelength modes would be anisotropic as well as having a power deficit. There seems to be a way of explaining killing two birds with one stone with one mechanism, with the power deficit and the anisotropy. But I'm afraid the Gaussianity and non-Gaussianity is something that I have to explore.
May I take issue with your claim about the conspiratorial fine-tuning problem in quantum mechanics in relation to the no signaling theorem?
Relation to no signaling?
The no signaling theorem, yeah. I mean, you put a lot of emphasis on the Bell theorem. Now, what does the Bell theorem prove? The Bell theorem proves that there's action at a distance in any deterministic hidden variable theory that returns the predictions of quantum mechanics. The Everett interpretation is not a hidden variable theory, and it doesn't appear to have any action at a distance in it. You might say, well, there's a good argument for non-locality that comes from the original EPR argument. If the theory claims to be complete, it should be non-local. But again, the Everett interpretation has a very natural way of getting around that particular argument. So I would say there is absolutely no conspiratorial aspect to the no signaling theorem in the Everett interpretation, and in fact I would say that that's one of its selling points.
Yes. So I think I agree that in the Everett interpretation, then there's an implicit assumption in these arguments that there's one world that we're looking at. If you in Bell's theorem, there is an implicit assumption that when you make a quantum measurement, only one outcome occurs. And so, all of this discussion and deduction that there's some kind of non-locality, Everett is a way of just avoiding that all from the beginning, as far as I can see, in which case, it is possible that I'm looking at this stuff, the phenomena, the theorems, the things we've understood or think we've understood, and I'm looking at it and thinking there's some kind of conspiracy, and that's only because, well, I'm stuck in this one world point of view, and that, if I adopted the Everett interpretation, all these uneasy feelings would disappear. I think there's a very fair point. So then one could, maybe get into discussion about, well, why do I not prefer the Everett interpretation? I mean, we could have that conversation, but basically I agree with you that I'm implicitly assuming one world. So.
Question? I've got a question I find I don't understand de Broglie-Bohm in a cosmological context. My understanding is there's a wave function of the universe, and there is just one configuration at one instant of time, and then that trajectory is completely determined for all time. And that I presume then that you can understand quantum mechanics for subsystems, because that's the way, if you look at individual subsystems, they will then be subject to quantum mechanics. But for the complete universe, I don't quite understand what it means to say that it starts off in in some superposition, I mean in some statistical distribution.
Yes.
And because it will always remain, whichever one it is, it will always remain one.
Yes, okay.
So I don't quite understand how the relaxation can happen.
Right, okay, yes, good. So this question here, you have exactly the same question in, say, for example, cosmological perturbation theory. If I go back to this kind of thing, one is talking about let us say the anisotropy in the microwave background. There is one sky. There is one temperature function with a certain anisotropy. There is one curvature perturbation here. There is one space-time back at this time with curvature perturbations. And yet cosmologists discuss statistics. Same with, distributions of galaxies. There's one universe with a distribution of galaxies, and yet people talk about, is it Gaussian, is it non-Gaussian? The way this happens, let me just say first of all that fundamentally I agree with you. In this theory, as in classical cosmological perturbation theory, there is just one universe with one configuration that's evolving in time and is very complicated. And this talk about statistics is some kind of effective way of dealing with a large number of degrees of freedom without having to follow all of the details. And the way that is done in cosmology in this context is through certain assumptions of statistical isotropy and homogeneity, which, I'll try to say a bit about that on Wednesday. That basically, I can say here that in this context, what happens, I look at one sky and I see one temperature function. So there's one set of coefficients here. And yet, you listen to cosmologists talk, and they're talking about whether these coefficients are Gaussian, non-Gaussian, the power spectrum, and what on earth is that all about? There's just one set of coefficients. What happens is, if you assume that this temperature function that we see is in some sense a realization of a stochastic process, which you could think in terms of a theoretical ensemble, or however you want to think about this, but there is a probability distribution in some sense for this temperature function. If you assume that that probability distribution is isotropic, in the sense that the probability for this temperature function is invariant under rotations on the sky, you can deduce that the probability distribution for these coefficients is independent of the value of m. And what that means is that, say, for instance, for L is 100, I've got 2L plus 1, that's 201 values of these coefficients that all come from the same probability distribution. And I can start meaningfully doing statistics. There's also an assumption of large-scale homogeneity, whereby you write this formula for the angular power spectrum. You have to assume that the probability distribution for the curvature perturbations is translationally invariant. This is how this is done, and that you can do, because the curvature perturbation is just proportional to the inflaton perturbation, one can do all of these same kinds of things at the level of the inflaton field, the de Broglie-Bohm trajectories. So let me say two things. The question is a good one, but it doesn't have anything particular to do with de Broglie-Bohm theory. It's the same in classical perturbation theory, all of these kinds of analyses. Okay, so the question is a good one, and it relates to all of these things. What do I think about the question? It seems to me an interesting topic, this, what do these things mean? Theoretical ensemble of universes, which, theoretical ensemble of skies for the CMB, the curvature perturbations. I don't have a strong view about this. Do I have to imagine that there's some actual ensemble of universes as in eternal inflation, and we're just seeing one patch? Can I take this as just some kind of effective way of talking to do with ignorance, best estimates? I don't have strong views about philosophy of probability or statistical inference. It's a good question, but it's a very broad question that's not particularly related to de Broglie-Bohm, I would say. Thank you. Thank you.